Okay. Right, the point that I made yesterday was that the subtle knowledge of how to deal with implicit functions is kind of the key to getting an extremely high grade. Now remember we said yesterday that if a function depends explicitly on x, it depends only on x, but x doesn't depend on anything else. Do you know what I mean? The difference when you have a function of y is that, okay, number one, you've got a function of y, but y itself also depends on x. Okay? Do you understand what I'm saying? So you have a function of a function which is bringing in a chain rule, which means that you've got to multiply by dy dx every time you differentiate a function of y. Okay? Now the real skill here is knowing how to switch from one to the other. Okay? That's the real cleverness here. So I'm going to put up some unusual questions and I'm going to find very sneaky ways of doing them and reducing the amount of difficulty. So imagine this. If I said to you, if e to the power of y equals 1 minus x squared over 1 plus x squared, find dy dx. Now I'm kind of leading you into this one blind. Okay, a little bit at the beginning. So if e to the power of y equals 1 minus x squared over 1 plus x squared, find dy dx. Now the function that you see on the board, would you describe that as implicit or explicit? It's implicit, isn't it? Okay, it's implicit because it's e to the power of y. Okay, there is a function of y, so it's definitely implicit. Now, what I'm wondering is, should I leave it like that and differentiate it implicitly, where I would have implicit differentiation on the left and I'd have the quotient rule on the right? Are we all agreed? If I differentiate e to the power of x, I get e to the power of x. If I differentiated e to the power of y, wouldn't I get e to the power of y dy dx? And then on the right hand side use the quotient rule. Wouldn't that be a totally valid way of doing that? Of course it would. But there's a better way. Okay, the better way is this. Imagine if we brought that exponential across the equal sign. What happens to a function when it goes over an equal sign? Becomes its inverse. What's the inverse of e? ln. So what's easier to differentiate? E to the power of y equals 1 minus x squared over 1 plus x squared, or y equals ln of 1 minus x squared over 1 plus x squared. Okay? Which is easier? The second one by a mile. Okay? The reason being this, that we know that the natural log of a over b equals the log of a minus the log of b. Okay? The log of a over b equals the log of a minus the log of b. Okay? So we can use that fact to remove the quotient rule from this completely. Okay? No more quotient rule here. So I could just say that y equals the log of 1 minus x squared minus the log of 1 plus x squared. Is that okay? Now, I presume everybody understands I can't get away without using the chain rule here. Okay, like in the first one, again, read it backwards. Function number 1 is 1 minus x squared. Function number 2 is ln. Function number 1 is 1 plus x squared. And function number 2 is ln. Okay? Now, if I work that out, I get dy dx equals, well, differentiating, what's going to happen to the first one? Minus 2x divided by 1 minus x squared. In actual fact, from here on, don't we have a question that we did the other day? Okay, this is basically yesterday's question. And then minus, when I differentiate 1 plus x squared, I get 2x. And when I differentiate ln, I get 1 over whatever came after log. So 1 over 1 plus x squared. So that goes downstairs. Okay? Now if I was to write that as a single fraction, I would have 1 minus x squared multiplied by 1 plus x squared. Okay? Now what would I do with the first minus 2x? Sorry, well on the bottom it will, but I'll leave that in the next line, Michelle. Okay? So you're trying to do 2 steps at once. You're far better off, just take your time, don't rush it. So first, the minus 2x on the left, I multiply that by 1 plus x squared. and the minus 2x on the right, and multiply that by 1 minus x squared. Are we all happy? Yeah? So next line, on the bottom, I agree 100%. Difference of two squares, 1 minus x to the power of 4. Okay? On top, I've got minus 2x cubed, minus 2x, plus 2x cubed. So what's my final answer? Minus 4x divided by 1 minus x to the power of 4. Okay? Minus 4x divided by 1 minus x to the power of 4. Are we all totally okay with that? Yes? So dy dx is equal to that. There we go, job done. Alright? Now, this has come up a few times, a carbon copy of this question, and remember, when you look at the Leaving Cert exam papers, you notice, I've said it before, on top of the differentiation question it says old syllabus. Have you noticed that? Old syllabus.
What is that like? Is that what you just did? It's not paramedic, it's not implicit.
Well, it was implicit at the beginning, but we turned it into explicit.
Yeah,
So we just basically
using rules of log.
Yeah. Whenever you get the opportunity, do you notice I've used logs a lot to do things in differentiation, even though you might have thought, when you're looking at the question, you think, how are you going to bring logs in here? But logs help a lot, because the rules of logs save you using things like the product rule and the quotient rule, because you can change multiplication into addition, and you can change division into subtraction. Okay, it's very, very straightforward. Now, what are we missing? Sorry, I have to think more. I forgot my role. Do you know, I don't think we're missing anybody. No. Okay. Everybody happy? Now, I think, as I said, the years that they ask it, they said write your answer in the form ax over 1 minus x to the power of n. Okay? Did I say to you write your answer like that, which means do the tidying up at the end that I did. Okay? Now that would have been on the old course. By the way, the structure of the questions for differentiation is still the same as it was on the old course. It's just a couple of things have been simplified. Okay? So still the same structure. Okay? Very, very similar structure. So that's why I've actually brought, I'm sorry, I brought in the wrong exam papers. The old exam papers are fine for differentiation and integration. Okay? The only thing, I suppose, in integration, substitution is gone. But in differentiation, the old papers are fine. Okay? The old ones, going back to 1994. Okay? Any questions on that? We happy enough with it? So the moral of the story is we love logs. Okay? Logs make life very, very easy in a differentiation world. Okay? So learn to love logs. Now, the final two jobs that we have to do to tick all the boxes in the how to differentiate section is differentiation of the inverse trigonometric functions. So sine inverse or tan inverse. You do not need to know how to differentiate cos inverse, not on the course. Okay? So sine inverse or tan inverse. So we'll begin with sine inverse x. If y is equal to sine inverse x over a, we'll say, let's actually prove this. Show that dy dx, does anybody remember what it's equal to? What do you get when you differentiate sine inverse x over a? 1 over the square root of a squared minus x squared. Okay? So show that if y equals sine inverse x over a, show that dy dx is 1 over the square root of a squared minus x squared. Now, at the moment, when you look at this function up here, would you describe that as being implicit or explicit? It's explicit at the moment. It depends explicitly on x. Okay? There's no function of y. Now, in the last question, I showed you that turning something from being implicit to explicit actually made the question easier. Now I'm going to do the reverse. I'm going to show you know what? It's not always about going implicit or explicit. Sometimes it's about either or. So this time I'm going to say, you know what? I don't know how to differentiate sine inverse yet. But I know if I brought that sine inverse across the equal sign, it will become, what's the inverse of sine inverse? Sine. So wouldn't I end up with sine of y equals, let's write it like this, 1 over a multiplied by x. Alright? I've written it like that for a reason, to make the next line a little bit more understandable. So are you happy with what I've done? All I did was bring sine inverse across, and the inverse of sine inverse is sine. Now, I know how to differentiate sine. If I differentiate sine x, I get cos x. What happens if I differentiate sine y? Cos y dy dx. So cos y dy dx equals, differentiate the right hand side. What happens when you differentiate 7x? 50x. 1 over a multiplied by x. 1 over a. That's why I wrote it the way I did. Is that okay? So it's just 1 over a. It's not the quotient rule because a is a constant. Okay? Now obviously in reality, sine of y is x over a. It was just easier to think of it like that. Okay? So doesn't that mean then that dy dx equals 1 over a cos y? Yes? Now, you're probably looking at that and thinking, well, you haven't really helped things, John, because this is 1 over a cos y, and over there we have 1 over the square root of a squared minus x squared. So it's not looking too nice. However, don't we know that cos squared y plus sine squared y equals 1? So if I mess around with that, wouldn't you agree that cos of y is the square root of 1 minus sine squared y? Isn't it? Yes? So if cos of y is the square root of 1 minus sine squared y, that means that cos of y is the square root of 1 minus x squared over a squared. Isn't it? Because sine of y is x over a. So sine squared y is x squared over a squared. So that's what cos y is equal to. Now, a cos y is then obviously going to be a multiplied by the square root of 1 minus x squared over a squared. Okay? Now what happens to a number when it goes into a square root sign? When I bring this a in here? Don't you have to square it? Now what's a squared multiplied by 1? A squared. What happens when you multiply the second part by a squared? A squared on the top and a squared on the bottom cancels out, and I'm left with the square root of a squared minus x squared. So a cos y is equal to that. So that's just using techniques from trigonometry. And then, talk to me, what's dy dx? 1 divided by a cos y, 1 divided by the square root of a squared minus x squared. There you go.
See the cos squared y plus sine squared y. Is that like
That's
cos
a
plus sine always with
the cos squared plus sine squared is always 1. Okay, as long as it's like cos squared y plus sine squared z is not equal to 1. But if the two angles are the same, it's 1. But it has to be cos squared plus sine squared. So cos squared theta plus sine squared theta is 1. Cos squared p plus sine squared p is 1. Cos squared q plus sine squared q is 1. Cos squared z plus cos squared y is not 1. Okay, do you know what I'm saying?
Yeah.
So we're happy then with how I proved that. And as I said, in this question, it was a good idea to change an explicit function into an implicit function. So as I said, it's not all about one and none about the other. Okay? Whenever I look at a C part of an even cert question, before I do it, I always have a quick think to myself, am I better off leaving the function where it is, or should I bring it across the equal sign? Do I end up with something that's easier to differentiate or harder to differentiate if I move it across? Now, if the thing you end up with looks easier, it's probably a good idea to go that way. And if you're, like whenever you see an E, not every time you see an E, but very often if you see an E, it might be a good idea to bring it across and turn it into log. Okay, because you could avoid quotient rule, product rule, all kinds of messing. Okay? Now, in reality, this formula here in that black box, it's really just a matter of looking it up in the log tables and using it. Okay, as I said, I did that as a demonstration to show you that implicit is good as well. Okay? So if y equals sine inverse x over a, dy dx is 1 over the square root of a squared minus x squared. So now let's do some examples. Right, number 1. If y equals sine inverse x over 3, find dy dx. Well, in my log tables, we have y equals sine inverse x over a, and we know that dy dx is 1 over the square root of a squared minus x squared.
Is that called the implicit rule?
No, it's just inverse trig. Okay, it's in the differentiation pages. Okay, you look up differentiation and it's near the end. Okay? All you got to do is compare. On the top here, I have an x. On the top over here, the formula has an x, so that's grand. That's good news. On the bottom here, I have a 3. On the bottom over here, there's an a. Okay? So, what does that say? Just a equals 3. Just put in 3 instead of a. So, in other words, all I got to do is say dy dx equals 1 over the square root of 3 squared minus x squared. Now, what's 3 squared? 9. 1 over the square root of 9 minus x squared. That's it. It's that easy. Just put in a number instead of x. Oh, sorry, instead of a. Now, I have to say, you really would be rubbing your hands together with joy if you saw that question in June. It's ridiculously simple. Here's one that's a little bit harder. It's kind of the next step up. If y equals sine inverse 2x over 3, find dy dx. Now again, our rule is if y equals sine inverse x over a, dy dx is equal to 1 over root a squared minus x squared. Agreed? The only thing is there is a significant twist in this question. Okay? It's not nearly as nice. Because we have a 2x on top, but the formula just has an x. Is that okay? Obviously, in terms of the number on the bottom, we have a 3 on the bottom. The formula has an a on the bottom. Okay? But unfortunately, there's a difference in the x's. Now, whenever there's a difference in the x's, that automatically means we have to start reading things backwards because the chain rule is coming in. Like it's if you differentiate sine x, it's just cos x. But if you differentiate sine 2x, don't you have to say the first function is 2x and the second function is sine? So we have to do the same thing here. We have to say the first function is the 2x function and the second function is the sine inverse function. Don't worry about the 3 because I can just put 3 in instead of a. Alright? So we differentiate each of those one at a time and I get dy dx equals, well, differentiate 2x for me, you get 2. Now, if you were to differentiate sine inverse x over a, you'd get 1 over the square root of a squared minus x squared, wouldn't you? But that's wrong here. What have I done that's wrong? It's not x squared, it's 2x squared, because you're putting in 2x instead of x. Okay, again, if you look here, I have a 2x, they have an x. So I'm putting in 2x instead of x. So when I tidy that up, my final answer is 2 over the square root of 9 minus 4x squared. Is that totally okay? So that's kind of a medium level. That's kind of taking a step up.
How did you get the 3 squared minus 2x squared?
Well, a squared minus x squared. What number is on the bottom? Whatever number is on the bottom is a. So that's where the 3 came from. And then the 2x, well, that's the top. That goes in instead of x. Is that okay, Adam? So we're all happy? Now, if I was to be honest with you, I think that this is the most likely type of question that they would ask. Okay, this mid-range one. The next one is chaos. Okay, this is really not nice. Okay? So for question 3. Now there is a fourth type as well that they have actually asked. Well, I'll come to that when I'm finished tan inverse. If f of x equals sine inverse x squared minus 1 over 4, find f dash x. Okay, now again, every time I use a formula, I write it down. If y is equal to sine inverse x over a, f dash, sorry, if f of x, because we've changed the labels, f dash x is going to be equal to 1 over the square root of a squared minus x squared. Okay? So if f of x is equal to sine inverse x squared minus 1 over 4, find f dash x. Well, again, because the top isn't just x, I've got to say that function number 1 be x squared minus 1 and function number 2 be 4. Sorry, not 4, sine inverse. Okay? Now, would you agree that x squared minus 1 is taking the place of x and 4 is taking the place of a? Is that alright? So here we go. F dash x equals, well, differentiate x squared minus 1 for me. 2x. Multiplied by, now do the sine inverse part. 1 over the square root of 4 squared minus x squared minus 1 squared. In other words, I'm putting in x squared minus 1 instead of x, and I'm putting in 4 instead of a in my formula. Is that okay with everyone? Adam, you okay with that? Now that's going to give me 2x on top, divided by an almighty headache on the bottom, 16 minus x to the power of 4, square the first, multiply the first by the second and double it, minus 2x squared, plus square the last. Is that okay with everybody? So when I square x squared minus 1, I'm going to get x squared minus 2x, sorry, x to the power of 4, minus 2x squared, plus 1. So my final answer is 2x over the square root of 15 plus 2x squared minus x to the power of 4. Is that okay? We all happy with that? So 2x divided by 15 plus 2x squared minus x to the power of 4. Now, interestingly, in this situation, we can do something here. We can do something quite clever, because I've spotted something with the numbers. Have you spotted anything? I can actually factorize the bottom. Okay? If you look at it, they might say write your answer in this form. So 2x over the square root of, well, the bottom is going to have a minus x squared and a plus x squared. It's going to have a 5 in here and a minus 3 over there. Sorry, plus 3. If you look at it, 5 multiplied by 3 is 15, minus x squared multiplied by x squared is minus x to the power of 4. 5 by x squared is plus 5x squared, and 3 by minus x squared is minus 3x squared, which is 2x squared. So they could ask you to factor it down like that. Okay, all I've done is just factorize that function. It's a bit of a weird function, though, I have to say, to factorize. Just in case they said write your answer in the form ax over b minus x squared multiplied by c plus x squared. Okay, just in case they'd say something like that, which they could do. Okay, but if they do, it'll be clear. If they just said differentiate, what you had here is perfect. Okay, but if they said write it in that particular form, for whatever reason, you'd have to go ahead and do it. Okay. So we all happy enough with sine inverse? Yep. Well, now tan inverse is going to be a breeze, because the exact same, it's going to be boringly similar. Everything we did to sine inverse, we're also going to do to tan inverse. Okay? So we're going to do 3 types of questions. If y equals tan inverse x over a, dy dx is equal to a over a squared plus x squared. Okay, a over a squared plus x squared. And again, is that formula written in the log tables? Absolutely. Okay, absolutely. Again, at the end of the differentiation section, it's there. Right, now, can you try to prove that for homework? What do you think you're going to do? How did I do sine inverse? Bring the tan over, it becomes tan. And what do you get when you differentiate tan? You get sec squared, which is really 1 over cos squared. So just give it a go for homework. It's not the end of the world if you don't get it out. We can have a look at it tomorrow. Okay? Now, anyway, level 1. If f of x equals tan inverse x over 5, find f dash x. Well, I'm not going to write down the formula again because it's right beside us. Would you agree? All I got to do is put in x instead of x, so no chain rule. Okay? And instead of a, I'm going to be putting in 5. Okay? The bottom, 5.
If you have to divide that formula, will you be asked?
Yeah, but I'm asking you to do for homework and then we'll do it in class then when we come in on Thursday. I just want you to struggle your way through it. So f dash x equals, right, well, what am I putting instead of a? Isn't it going to be 5 divided by 25 plus x squared? There you go. Where did the 25 come from? How did that appear on the page? 5 squared. Now, isn't that easy? Now, I promise you that without my help, you're going to be able to do this question. If f of x equals tan inverse 3x over 4, find f dash x. Off you go. Give it a go. Give you a few seconds head start. Is this a straightforward tan inverse or is it a chain rule version? Chain rule, isn't it? So function number 1 is, and function number 2 is tan inverse. So go on, what's f dash x? Differentiate my 3x function. 3. Differentiate the tan inverse bit. Now be careful. Remember what you're doing is you're putting in 3x instead of x, and you're putting in 4 instead of a. Is that okay? So 4 instead of a and 3x instead of x. So that's going to be 4 instead of a divided by 16 plus 3x in brackets squared. Is that okay? So f dash x is equal to 12 divided by 16 plus 9x squared. Again, that's the kind of question I would expect to see. They tend to hit the medium level. Okay? And because they are simplifying the course, I would expect to see a question like that. Okay? Now, if they want to really challenge you, they could go along this line. This is a question from about 6 years ago, an exact question. Okay? So here goes. If f of x is equal to tan inverse x over 2 and g of x is equal to tan inverse 2 over x, find f dash x and g dash x. Well, you'd argue that one of those is an absolute walk in the park, isn't it? Which one? f dash x. Okay? So for f dash x, we just go f of x equals tan inverse x over 2. So f dash x is going to be 2 over 2 squared plus x squared, just putting in 2 instead of a and x instead of x, no chain rule, no messing. So f dash x is very simply what? 2 over 4 plus x squared. There we are. Next, much harder over here. G of x is equal to tan inverse 2 over x. Now here's a kind of a rule that you need to take home. Do not leave x underneath the division line. Is that okay? Do not leave x underneath the division line. Isn't that really tan inverse 2x to the power of minus 1 divided by 1? Yes? Isn't it the same thing? Aren't those two functions the same? So what have I done? You see, what I've wanted to do is I've wanted to have a constant on the bottom. There you go. Isn't a equal to 1? Yes?
Can you bring the x in front of the front?
Absolutely not. You can't. It's buried in a tan inverse function. You can't get at it. Okay? Now, obviously, on top, haven't I got 2x to the power of minus 1 where I should just have x? So, what would the chain rule have to say about this? First function is 2x to the power of minus 1, and the second function is tan inverse. Now, remember, 2x to the power of minus 1 is really just 2 over x, isn't it? Just written a different way. So here's the argument that I have. For differentiation purposes, I prefer this form, 2x to the power of minus 1. For use in the tan inverse formula, I prefer this formula because it doesn't have any negative powers. So anyway, talk to me. G dash x. Differentiate that first function. Bring the power down in front and reduce the power by 1. What do you get when you differentiate 2x to the power of minus 1? Minus 2x to the power of minus 2. So hasn't that come from differentiating this bit? Is that okay? Next, what about the tan inverse part? The tan inverse part is going to be a over a squared plus x squared. A over a squared plus x squared. Now a is just 1, isn't it? So the top is easy. It's just 1 over 1 squared, which is 1, plus, what am I putting in instead of x? 2x to the power of minus 1, or 2 over x. It might be easier to put in 2 over x, wouldn't it? Easier to write. So divided by 2 over x squared. So that came from differentiating the tan inverse bit. Is everybody 100% okay with that? I only wrote it as 2x to the power of minus 1, so it would be easy to see what this bit was. Minus 2x to the power of minus 2. From the point of view of sticking something in instead of x, it's easier to shove in 2 over x than it is to shove in 2x to the power of minus 1. So I was literally using whichever form suited me in each place. Are you totally okay with that? Okay? So that means then that g dash x equals, now this bit here at the start, 2x to the power of minus 2, isn't that really minus 2 over x squared? Multiplied by 1 over 1 plus 4 over x squared. And let's just be careful, put in brackets so we don't do anything daft. Okay? So, final answer. G dash x equals top multiplied by top, bottom multiplied by bottom. What's minus 2 multiplied by 1? Minus 2. Now multiply the x squared through. X squared multiplied by 1. So x squared here multiplied by 1 there is just x squared. Now what happens when you multiply x squared by 4 over x squared? You get plus 4. Is that okay? So there's g dash x. Much harder to get g dash x than it was to get f dash x. Is that okay? Much, much harder. We all okay with it? Now here's the interesting bit. Part 2. Show that f of x plus g of x is constant. In other words, i.e. tan inverse x over 2 plus tan inverse 2 over x is constant. Hence, or otherwise, show that that's true. Any takers? Differentiate 50. Differentiate a million. Differentiate 0.675. 0. What happens when you differentiate a constant? You get 0. So if you differentiate a constant, you get 0. Right, well if you differentiate f of x, don't you get f dash x? So f dash x, plus g dash x. You see, if you differentiate f of x plus g of x, you get f dash x plus g dash x. That's called the addition rule or the sum rule. Isn't that 2 over 4 plus x squared minus 2 over x squared plus 4? But sure, minus 2 over x squared plus 4 is the same as minus 2 over 4 plus x squared. Do you notice that the two of those are identical? Just opposite in sign? So what's the answer? 0. Now tell me this, is it always 0 or is it just 0 for some specific values of x? It's always 0. No matter what x is, that's always 0. So f dash x plus g dash x is always 0. So if you differentiate f of x plus g of x, you get 0. So what does that say about f of x plus g of x? It's constant. Okay, f of x plus g of x must be constant then. Because no matter, if you differentiate it, it doesn't matter where it is, the answer is always 0. So f of x plus g of x must be constant. Okay, so just write this down.
You differentiate them again, but does that give you a line and one goes in one direction and the other goes in the other direction?
Well, if you put the two together, that's kind of what happened. Well, not a line, but two curves are adding together to give a line. That's what's basically happening. A flat line. Okay? So just write this down. Since the derivative is 0 for all values of x, not just for some special values, since the derivative is 0 for all values of x, this means that f of x plus g of x is constant. This proves that f of x plus g of x is constant. So if you're ever asked to prove that something is constant, all that means is differentiate it and prove that your answer is always 0 no matter what you put in for x. Okay? Again, are we clear on what I mean by that being 0 for all values of x? I didn't have to see for what values of x is it 0. I saw that no matter what you put in instead of x, it's going to be 0 because the two fractions are the same. Okay, so it's permanently 0. So we're all absolutely, completely, 100% okay with that. Okay? That's brilliant. So therefore, f of x plus g of x is constant. Now after they asked that, there was something trigonometric that you were asked as well, but it's no longer on the course, so you don't need to worry about the third part of the question. Okay? It was actually a trigonometry question. They said, okay, now it's constant. What is its value? Is it 57? Is it 32? And that's a trigonometry question, not a differentiation question. But that part has gone off the course. Okay? So are we entirely happy with that? Now the good news is that's how to differentiate. Okay? There are no other functions that you need to know how to differentiate that it need bother you. Okay? Now I'm going to throw in, this is one thing, this is a question I do every year with students, and I'm always doing it as a just in case. You look through any Leaving Cert papers, you will never see this question. But I'm just suspicious that eventually it's going to come up, and I don't want to be caught out one year. So I'm going to throw it at you as a just in case. Alright? So just because it's never come up doesn't mean it's That doesn't mean it's not important. Okay? If y equals, Sean, pick any number between 2 and 5. 3. Sorry, I was about to write f dash x, which would be a mistake, wouldn't it? Because I've called it y, I'm going to be looking for dy dx. Okay, have a little think about it. See how you get on. If you were confronted with that in the leave insert, what would you write? The answer, by the way, is about 4 lines. Really quick. And they're short lines. So give it a go. See what you can come up with. You see, if you differentiate e to the power of x, you get e to the power of x. But if you differentiate 3 to the power of x, you don't get 3 to the power of x. It only works for e. Is that okay? That non-changing only works for e. So the question is, if you differentiate e to the x, sorry, 3 to the x, what do you get? And again, it's just a really clever trick. What's the only type of log that we know how to differentiate? ln. Log to the base e. And you see the problem is if I bring 3 to the power of x across the equal sign, it becomes log to the base 3, doesn't it? But we don't know how to differentiate log to the base 3. We only know how to differentiate log to the base e. So bringing the 3 to the power of x across the equal sign is not going to be the solution. Okay, because it produces a log that we don't like. Okay? However, we do have a log that we do like, don't we? What log do we like? ln. We want ln. So let's go for ln. Sorry. Right. If y is equal to 3 to the power of x, doesn't that mean that the natural log of y is going to be the natural log of 3 to the power of x? Yes? Now the question is, why was that beneficial? It's a stupid idea. No, if you said if you use log to the base 3, it won't be useful. I didn't say logs. I said if we're going to use logs, it has to be ln, because they're the only logs we know how to differentiate. Okay, what I said, I'm fairly sure that I said log to the base 3 is no good to us. Okay, so what I've done is I've just taken the log of both sides. But you see, I have this little formula that says that log of x to the power of n equals n log x. So can't I now say log y equals x log 3? Yes? Differentiate the left-hand side for me. 1 over y, dy dx. Why is there a dy dx tagging along there? It's implicit differentiation, isn't it? It's a function of y, and y is a function of x, so I need to multiply by dy dx. Differentiate 50x for me. 50. Now differentiate x multiplied by log 3. Log 3. Log 3 is just a number. The log of a number is just a number. It's just a constant, so it's a constant multiplied by x. And if you're differentiating a constant multiplied by x, you just forget about the x. Okay? Now, that means then that if 1 over y dy dx is equal to the log of 3, that means that dy dx is equal to y log 3. Yes? Just multiply across by y. But sure, isn't that equal to 3 to the power of x multiplied by the natural log of 3? Because look back up here, isn't y equal to 3 to the power of x? If you just left it as y log 3, oh yeah, they wouldn't like that answer at all. Okay, they would want 3 to the x log 3. Now, as I said, that's an example. If you said to me, what have they never asked, that you have a sneaky position that, or suspicion that they could ask, I think this is it. It's incredibly short, but just taking that intelligent step to take the natural log of both sides, that's key to the question. Okay? And now, as I said, you can pretty much differentiate any function that you might need to differentiate. Okay?